In the settings menu, there's a section devoted to soil models and to bedrock parameters. But what are soil models? Soil models are the conceptual basis on which the subgrade's nonlinearity and presence or absence of bedrock are considered by the back analysis algorithm, which is the same thing as to say that the soil models are the way that the geotechnical conditions of the site where the FWD tests were executed is depicted in the back calculation algorithm. DAPS has two major families of soil models, those that include bedrock at a certain depth and the soil models that do not include bedrock at a certain depth. Looking at the soil models with bedrock, there are two possibilities. One is the constant depth to bedrock, in which a stiffer layer or a bedrock layer is considered at a certain depth, but that depth is constant. Is the same, which is the same thing as to say that from the first FWD station to the last FWD station, the distance that is considered to where we can find the bedrock is constant. Then we have its opposite, which is the variable depth to bedrock model, which also assumes the stiff bedrock layer at a certain depth. However, this depth is variable and calculated by DAPS itself, while for the constant depth to bedrock, we can define that or impose a certain value for the depth at which the bedrock is found, just as well as the stiffness of the bedrock layer. So we can assume it to be 5,000 megapascal, 10,000 megapascal, the number that we see fit, and the number that proves to be best. And we also have three soil models that do not consider bedrock, namely one in which the subgrade is considered to be of constant property. So no matter how deep we are in the subgrade soil, the stiffness remains constant. Then we have the Gibson soil model that assumes that as we go deeper into the subgrade, that the stiffness increases and that the increase in stiffness is um, directly proportional to the depth which we are considering. And we have the SDS or stress dependent subgrade model, which just like the Gibson soil model assumes that there's an increase with stiffness as the depth increases. But this, in the case of the SDS model, the increase in stiffness is not linear, so it's not directly proportional to the depth. It's an exponential increase if you want to consider it that way. So these soil models are depicted here. We have the known half space soil model, which is this one here. We have the constant depth to bedrock and variable depth to bedrock, which are the two that consider bedrock at a certain depth. And at last, we have the stress-dependent subgrade model and the Gibson soil model. We also can define, in the bedrock parameters, we can define the depth at which the bedrock is located. However, this value will only be considered if we are using the constant depth to bedrock model. And we can also define its stiffness, so to say. The standard or the default value is 1000 megapascal, but we can increase it or decrease it as we see best. Um, and how do the soil models influence the back analysis? So let's pick a random drop. You notice that when we have the pavement section correctly defined and we select a particular drop from the list, these buttons become visible, and each of these buttons corresponds to a soil model. So I can back calculate this particular drop using the KHS model, the known half-space model, and I'm going to obtain a particular result. Then I can back calculate exactly the same drop using the CDB model, or the constant depth to bedrock model, and I'm going to get a different result. And every time that I select a different result, a different model, I'm going to obtain a different solution. So you might ask, and what is the appropriate soil model? The appropriate soil model is the soil model that the most appropriate soil model has to comply with two major parameters. One parameter is the statistical analysis of the error. So in this case, we have a root mean square error of 3.07% and an absolute medium deviation of 8.51 microns, which means that this is an excellent solution. So the statistical analysis of the error is very important. However, there is another factor that we must take into consideration. We have to verify the result and make sure that they are in accordance to the materials that are embedded in the pavement structure. So if I go to edit, I can see that I have an asphalt concrete layer, that I have a seed modulus for the concrete layer of approximately 2,200 megapascal, that I have a granular base with a seed modulus of 132, and a subgrade seed modulus of 66. So all these values here are acceptable values for the materials that we are considering here, an asphalt layer and a granular base, and so are these. So we can say that this is a good solution because it complies not only with the statistical analysis and with the low error, but it also complies that in the term that the back calculated moduli coincide with the values that are contained within the interval of magnitude that are usually associated with the materials that are built into the pavement structure. So this case that I'm considering for this particular sample file is particularly benign because I can back calculate the the the, the FWD test considering any particular soil model, and I'm always going to get reasonable results both in terms of statistical analysis and also of the magnitude of the layer stiffness. However, this is not always the case. There are some, or most of the times, this is not the case. Let me correct. Because what happens is that um, um, usually there's one particular soil model that proves to be the most appropriate one, and we can use this drop to drop um, this the capability of back calculating drop by drop to get a sense of what is the best soil model that we can use for the batch analysis process that begins here, and that will use the soil model that we select in this list. So first we have to verify which of the soil models is best using this option, for example. Then we have to select it from this list, and only then will we run the batch analysis with the soil model that we uh, see best. And let me add that there's one more thing that we can do. We can come here to the single test and select the option drop from list, which is something that we still haven't done in these videos. And when I select drop from list, there is the drop that is being considered here. It's this one exactly. So I can back calculate it drop by drop using this particular capability, or I can back calculate it here. And I can also verify which of the optimization routines is better, simplex or damped square. So in this case, we have an error of 2.64%, and if we select the damped squares, we have an error of 0.98%, and the calculated layer moduli are excellent and within expected parameters. So this is a very good solution with an extremely low error.